windows or tabs do they have open? What sort of crazy JavaScript is running? So it's impossible to know what the heap looks like when the victim shows up on your malicious web server. But what you can do is you can make them run JavaScript, and with that you can sort out the heap for them. So the heap basically, I described it's really complicated, and it's all fragmented to pieces, but it's totally deterministic, right? It's not magic. The basic idea, it's complicated of course, but the basic idea is that each new allocation will show up in the first spot that it can fit. So the way that you take over with a JavaScript bug on iPhone or any WebKit-based browser is basically these 5 steps. So first, you defragment the heap by filling in all the holes. Then you create a bunch of allocations, free up every other one, and then put in application data in the buffers you control. And then you overflow your buffer. So if you do those 5 steps, you end up overflowing application data that you control, and then you can access and get control of the whole process. So I'll explain that in a little more detail here, and then I'll show it in real life. Okay, so how do you make these allocations? Well, there's lots of ways. Any way that you can force the browser to call malloc, basically. So maybe in an image, HTML. We're going to talk about JavaScript. That'll fill in any holes. You just keep allocating the same size that you plan on allocating eventually. You don't know where they are in memory, but eventually you know they're going to be next to each other. And then you free every other one. And then you know the next time that, again, you don't know where this is on the heap. You just know that there's these holes on the heap. And then the next time that allocation of that size is made, it's going to fall into one of your holes. So Dino knows that there's not a whole lot of protections on overflowing heap metadata on a Mac, but there are some. It's basically easier to overwrite application data if you can than heap metadata. So by making those holes, we make sure that we control the buffer that's being overflown. So if we put data there and then access it, we'll be accessing corrupted data. So this is some bytes. These bytes are actually from Safari, as opposed to mobile Safari. And this is what it looks like in memory when in JavaScript you call new number of something. So in JavaScript, number, it looks like that. I don't have a pointer, I don't think. But so basically what you get is 1, which is the number of things in your array, right? Then you get the next thing is something about sparse arrays, which this isn't, so it's 0. And then you get a pointer to your number object. So here's a buffer that if I overflow this pointer to a number object. And I guess I'll say a little bit more. So I overflow this pointer to a number object. This number object has a function pointer within it. So all I have to do is reference this number pointer. When I override it, instead of pointing to a number object, it points to some buffer I control. And then when it tries to call that function pointer, instead of calling the function pointer, it's calling a pointer I control, and I get control of the process. So that's how this heap punctuation stuff works in JavaScript. Okay, so I mentioned that I had this exploit, and this is the one I was talking about, that it worked on the desktop, and then I wanted to port it to the iPhone. What changes did I have to make? Well, obviously I had to change the shellcode and the no upload stuff because it's a different processor. If you don't know that, you're in trouble. What else did I have to do? Well, I had this huge sled, like a huge no-op sled into my shellcode, and it used to be 1, 2, 3, 4, really big, right? And then I reduced it by 1 less 0 because it was too big before. If you tried to make a sled as big as I was doing on the desktop version, the iPhone would just quit and would bail. That's fine. The result is, though, that the area that you can land in is smaller, and so your exploit becomes less reliable. But it still works. Likewise, I talked about how in the feng shui you have to allocate a ton of buffers, right, to fill up all the holes and then to make the ones on the end that are adjacent. Well, on the desktop version, I allocated 1,000 of those buffers. I couldn't do that on the iPhone version because, again, I ran out of resources. So instead, I only allocate 100 buffers. And again, what this means is if your heap is really defragmented, like you have more than 100 of these holes to begin with, then the exploit's not going to work. So you end up with a less reliable exploit on the iPhone than you would on the desktop. The other thing which I didn't actually mention was there's this problem in JavaScript. You can't necessarily force a free because of garbage collection. So what I did was I just called sleep, basically. And that made sure that the garbage collection happened. Again, I couldn't sleep for as long on the iPhone version as on the desktop version. What else is different on when you write iPhone exploits as opposed to desktop exploits? Well, the actual overflow is a little bit different. The overflow was based on a regular expression, and so that was a little different. Also, the way the memory looks is slightly different. So they had used an older version of JavaScript. So remember before I said on the desktop version it looked like 1, 0, and then a pointer. Well, if you look at that top little excerpt from GDB, actually, it's not GDB, it's some other debugger. But anyway, now instead of that, it just looks like it's just a pointer. And so there's not that little bit of metadata beforehand. And then if you look on the second little set of numbers there, that's what the number object looks like. And so you can see there's a pointer and then some number and some zeros and stuff. Well, that first pointer is actually pointing to code. So that's the function pointer that I want to get called. So that's it. So there's not that many differences when you want to port the exploit. Just have to be careful for resources, basically. And then this is a slide that talks about so when you first start putting these buffers in the feng shui, right? They're filling up holes. They're all over the place. But eventually, I said I allocated 100 of these buffers. By the end, they start lining up right next to each other, which is what we want. And here is an excerpt from a debugger, and you can see that they start lining up right next to each other. So the first buffer is allocated at 975 something. And then the next one's at 976, and then 977, excuse me. So this is just showing that the feng shui stuff that I originally did on the desktop works on the iPhone too. Okay, so the takeaway from all that stuff is if you can write an exploit for the desktop, you're probably in pretty good shape for the iPhone. What about payloads? So payloads is much different on the iPhone. There are a couple payloads that Metasploit you can get. Most of those, I think, depend on the iPhone already being jailbroken. For non-jailbroken case, so like your typical person with a phone, you can still do anything, right? So your code is still running. You can call any system calls you want, whatever. But you have to so you can't rely on anything being there. So you can't rely on there being a shell or being whatever other program you might want to call. You basically have to assume there's no programs there that you want. So you just have to bring along all your functionality with you. And the other thing is, originally the iPhone ran everything as root, which was really stupid. Now they do something like only slightly stupid. So now they have two users. One called mobile, which does everything like you would ever want to do, like web browser, mail, text message. So that all runs as user mobile, and then the sysadmin stuff, that runs as root. So now when you break in, you get user mobile instead of root, but you still have access to basically all the data on the phone. The only thing you can't do is you can't try to jailbreak the thing on the fly anymore, which is probably why they did this, not for security, because they didn't want people jailbreaking their phones so easily. All right, so there's going to be tons of code coming up here. So let me just introduce you to ARM real quick if you haven't ever seen it. So in ARM, they have there's 16 32-bit registers that are called R0, they're R15. The last three have special names. So R13's the stack pointer. 14 is the link register, which is used to store return addresses sometimes. R15 is the program counter, and that's what you think it would be. ARM is a RISC architecture, so that means there's not as many different kinds of instructions as there is on x86, for example. And they're all 4 bytes long. And since they're 4 bytes long, and most of the addresses are 4 bytes, that means that generally to put a full D word into a register takes more than one instruction. Not that big a deal. There's also this thumb mode that ARM processors can do, but I'm not really going to talk about that. Okay, so how do function calls work on ARM? Well, instead of jump and call, you can get B, BL, BX, BLX. So it's branch, and then BL branches and sets the link register to the return address, so you can get back to where you started. The other thing is that on ARM, this is kind of cool. PC is just a general purpose register, so the program counter. So you can actually move stuff into the program counter. Or if you want to know, like shellcode usually needs to figure out where it is in memory, so you can just like read right out of that register. You don't have to do any crazy, jumps and pops and stuff. As far as function calls, the first 4 arguments are passed in the lowest registers, and any more beyond that are passed on the stack. What about system calls? Well, there's this SWI128 instruction, and that's what you call when you want to do a system call. You put the call number in R12, and then just like function calls, any arguments to the system call go in the low registers or the stack. So those 3 instructions are the equivalent of calling exit 0. So exit is, the syscall is 1, exit of 0, so the first argument goes in R00, and then you call SWI128. Okay, so what is some shellcode? So now I'm going to do like some payloads, and then I'll do some demos of, actually, I'll do a couple demos. So, well, one thing you might want to do, and this is what the very first shellcode I wrote did, you might just want to steal all those files I talked about off the person's phone. And I don't know if you can tell, but this image is like from one of those places where you have to pay to get the image. Otherwise, it has the water stamp on it, or watermark, I mean. So I thought it was funny that I'm talking about stealing files, and I use an image. Anyway. So what's the shellcode going to do? It's going to run. It's going to call back to the bad guy's server, and then it's going to open some file like the SMS database, read from the file system and write to the socket, close up, and you're done. So you can do this whole shellcode just with system calls. So this shellcode works on a jailbroken phone or a non-jailbroken phone. And there it is. It's a lot of assembly there. But if you look at the stuff that's, and again, if you want a copy of any of this stuff, it's actually all there. So when you get the slides are going to be available on the website. You can either just cut and paste it or just send me an email, I'll send it to you. So you can see all the system calls here, though. So it's socket, connect, open, read, close, write, close, exit. It's pretty simple. It's pretty straightforward. Okay, so what's something interesting about ARM? If you take that shellcode I just talked about and you write out the bytes for the machine code for it, you see this funny thing that, in every 4th byte is E something, right? And that's not a coincidence. So that's a good trick for if you're just, you're just like looking through memory with GDB or something, you can find what's machine code and what isn't just by this trick. And the reason that you get this is on x86, for example, there's these conditional instructions, like you could jump not equal, right? So this has to do with whether a condition code's true. Well, in ARM, every instruction has this ability to either execute or not. It turns out that the E means always execute. So those are instructions that aren't conditional, and that's usually what it is. So there's not that many times that you're just your typical instruction. They have to be super optimized to really take advantage of that. So usually you see all these E's every 4 bytes. Okay, so what about some shellcode that's a little more specific to the iPhone? Well, what if you want to do something with the phone, like itself, right? I could have stolen files from a desktop, but I can't like dial the phone, for example, if it's a desktop. Well, what about this? So you can just call right into the iPhone libraries that are on the device. So you could get the GPS and text messages, whatever you wanted. The way that I do this one is I call a function called audio services play system sound. The shellcode I'm going to show you is pretty lame, and it has that address hard-coded in. In a few slides, I'll talk about how you can not do that. Okay, so how do you know what the arguments to this function is? Well, thanks to IDAPRO, I disassembled mobilephone.app, and I figured out what happened when a text message came in. And you can see what happens is it sets this value 3EA in the register R0, so that's the first argument to the function, and then it just calls the function. That's it. It's very easy. And if you look around for other instances that calls, it just puts in different arguments for different things, but 3EA just means beep and vibrate. That's what happens when you get a text message. Okay, and here's the shellcode. It's real straightforward. All you do is load the address, and you load 3EA into R0, the address into R7, branch to R7. So branch is like call in x86, and then you loop and do it over and over and over again. Okay, I'll show you my demo. So this is a phone. It's running an old version. So this is running version 1.1.4. So this is the one that the regex bug still works on. So I'm going to exploit